Mathematics for Engineers. In this video, we're going to take a careful look at this book. It is titled Matrix Algebra for Engineers. It was written by James M. Geer, and William Weaver Jr. Now, this is a book that I talked about before, but in this video, we're going to take a closer look at this book and its contents, some of the mathematics in this book. This stuff is important. I have seen a lot of matrix algebra used in research papers in engineering type mathematics. So let's go ahead and take a look at this book. I'm going to zoom in here so we can see a little better. Matrix Algebra for Engineers. Nice book. University series in applied mechanics, solid mechanics, fluid mechanics, theory of structures, and applied mathematics, edited by James M. Geer, Stanford University. Really, really good school. Very nice. And this is an older book. Don't think it's new. This is much, much older. This is from 1965, right? Super, super old book from the 60s. Let's read what it says here. Matrix algebra has assumed a role of great importance to engineers because of the many useful applications of this branch of mathematics in various fields of engineering and applied science. Subjects such as electric circuit analysis, engineering mechanics, structural analysis, and systems analysis require the use of matrix operations for solving complex problems. Therefore, students of engineering need to obtain a working knowledge of matrix algebra as part of their basic engineering training. This book is intended to fulfill the needs of such students and others who wish to learn the elements of matrix algebra from a practical point of view. A working knowledge of the subject can be obtained from this presentation. Awesome. Either through self-study or in conjunction with classroom instruction. So the authors of this book assume that an individual could go out there and buy this book and use it to teach themselves matrix algebra for engineers, right? So that's a key point that is made here in the preface. And it's a big deal because it's 1965, right? And that matters because the types of books that were being written then are not like the types of books that are being written now. Today, modern math books are much more friendly. So a lot of the books back then were really hardcore. There are some really hardcore books from the 60s. The only mathematical prerequisite to studying most of this book is algebra, and the subject matter can be mastered easily by college students at all levels. Hardcore. Again, they're basically saying anyone can learn algebra. Methodology is emphasized rather than the mathematical structure of the subject. Nice. All right, so let's go ahead and take a closer look at the actual contents of this book. Let's look at the contents. The pages are rather thick. They're thick pages. It feels like there's a page in between, but like there's not. It's a thick page. So I got to give it a whiff here. It's calling me. Oh, smells amazing. All right, let's look at the contents of this epic book. Scalars and vectors. So this is something that is very easy to learn. You can easily learn about scalars and vectors, no problem. Again, basic algebra, yeah, you got this. Most people watching this video, I think in theory, could buy this book and like learn the basic stuff here, which makes it really cool. It's accessible, right? Like the last thing you want to do is pick up a book and then like you can't read the first page. That happens a lot with math books. Certainly not with this one. We're going to take a look at that later. Matrices, another really cool subject. Determinants, and then we have the inverse of a matrix. So all really basic things, but it's important, right? It's very, very useful stuff. Simultaneous equations, eigenvalue problems, and then coordinate transformations. And then you have some references and answers to problems and an index. So let's take a look here at the beginning. Chapter 1 is Scalars and Vectors. This is kind of cool. It's a book from 1965, right? So cool. Scalars. Before beginning a discussion of matrix algebra, it is useful to review the concepts of scalars and vectors. A scalar quantity is one that can be identified by a single number. For this reason, the numbers themselves sometimes are referred to as scalar numbers. An example of a scalar quantity or scalar is the speed of a vehicle, which can be specified completely by a single number, such as 60, provided that the units for the number, such as miles per hour, have been specified also. Interesting here. When stating the speed of a vehicle, there is nothing implied as to the direction of motion, correct, right? Nor whether the speed is increasing or decreasing. Other examples of scalars are the distance between 2 points in space, the temperature at a particular location in a room, and the number of storage locations in the memory of a computer. Wow, we're talking about computers in 1965. So cool. In each of these illustrations, a single number is sufficient to specify the quantity. For example, the numbers in the units might be 6 feet, 70 degrees Fahrenheit, and 32,000 storage locations, respectively. And it talks about vectors, and it introduces that concept here. And again, very, very easy. Let's skip ahead to another part of this book. So let's keep going through this chapter. So you see there's the second page. So it's not long. It's got a modern layout or a very classic layout. Things are in bold. It's just very clean, nice graphics. Really well done, especially for 1965, right? So this is an older book. And I keep emphasizing that because it's actually very readable and it's very good. Let's take a look at this. This is something that's important and interesting. A little piece of mathematics here. A unit vector is a vector having a magnitude equal to unity, as in the case of the unit vectors i, j, and k in 3 dimensions, right? So I here would be the vector whose first component is 1, and second component is 0, and third component is 0. J, again, is a vector in 3 space. All the components are 0 except the second component, which is 1. And then K, the first 2 components are 0, the third component is 1. The process of obtaining a unit vector in the same direction as any other vector is described in the next article. Yeah. So, yeah, you can always find a unit vector in the direction of another. You just find the magnitude of your vector and take your vector and divide it by the magnitude, and you basically normalize it. It turns it into a unit vector. And yeah, this is really cool stuff. Oh, look, here it is. Look, orthogonal and normalized vectors. So yeah. Oh, here it tells you. This is cool. Look at this. A normalized vector, okay, so they're calling it a normalized vector. So yeah, we're normalizing the vector. So a normalized vector is a vector of unit magnitude that is obtained from another vector by dividing every component of the vector by its magnitude. Right, absolutely. Thus, the normalized vector is a unit vector having the same direction in n-dimensional space as the given vector. Key point here, he says n-dimensional space. So that comes up like in research papers and stuff. I've seen this type of stuff, right? So it's good mathematics. It's math that's worth learning for engineering, if you're going into engineering. And, oh, here, matrices. Oh, here's the exercises. Here are some exercises, you see. You have exercises here. And then in the back of the book, let's look in the back, you have some answers to the exercises. So 1.46, let's look at this really quick because I want to show you something really important here. If we take a look at 1.46 right here, it says, show that the scalar product, okay, so it's one of those problems where you're asked to show something. So let's see, I don't think they provide solutions for those types of problems. Yeah, you see 1.46 is missing, but the other ones, most of the other ones are there. So the answers in the back of the book include most of the answers, except the ones where you have to show proofs and things like that. And that's common in books. So if you ever pick up a math book and you look in the solutions, and you notice there's only a few problems missing, that's probably the case. The ones that are missing are the ones where you have to show or prove something. But pretty cool book. One of the really cool things about self-study is when you are doing self-study, you can learn on your own and you can learn at your own pace and it stays with you. For some reason, when you pick up a book and you start learning mathematics on your own, it tends to stick with you a little bit better. And when you find books like this, that are written at a level to where the author's intent is that it can be used either in a classroom setting or it can be used for self-study. I think that makes it extra cool. Oh, let's take a look at this here in the back. Matrix Algebra for Engineers. This is so old school. Even the color. I just gotta give it a whiff here. Just, oh, smells amazing. Smells amazing. Matrix Algebra for Engineers fulfills the need of engineering students and practicing engineers who wish to learn the elements of matrix algebra from a practical point of view. Covering the topics of common interest to all engineers, this book presents the fundamentals in a clear and logical sequence, which is easy to follow. Explanations are accompanied by illustrative examples, and many problem sets with answers are provided for the benefit of the student. The subject matter may be easily mastered by college students at all levels, either through self-study or as a part of a formal course. Really cool. And here it talks about the authors. So Geer is a professor, now this was in '65, of structural engineering and associate dean of the School of Engineering at Stanford. Cool. There's other books he's written. And then here it talks about Weaver. Really cool. Yeah, wow. Wow, interesting, right? Very, very cool book. As a collector of books, this is pretty neat. This is neat. Coordinate transformations. This is also really important. Yeah, this is stuff that comes up in other areas of math. It's important because you see it again. You know, that's the thing, right? So that qualifies it, I guess, as important mathematics because you're going to see it again. You know, I've seen this. You see it in all sorts of places. For example, you first learn matrices. Many people first learn them in college algebra or pre-calc. That's typically in college where they're learned. And then determinants are often taught in one of those two classes, usually pre-calc, but sometimes college algebra. Yeah, and then eigenvalue problems, that's definitely learned in linear algebra. Same thing with coordinate transformations. A lot of these things here you do in pre-calc classes and stuff, Kramer's rule, but a lot of it's linear algebra like rank and stuff. And then this stuff, you see it in multiple courses, trig, calc 3, here's matrices, determinants, and then here's the inverse, again, something you might see in linear algebra or in a pre-calc class, maybe a college algebra class. So it's math that you'll see in multiple classes, so that's the cool thing. So when you learn from a book like this, I'm sorry, I just have to smell it again. You end up learning math that you see later, and that makes it extra cool. I know it's always a really good feeling, like when you see someone do something in math, and you're like, oh, I know exactly what that is because I learned it here, and this is X, Y, Z. And that makes it cooler. Yeah, that makes it really, really cool. Overall, this is a really good book that has a lot of mathematics that's useful for engineers, and I think it's pretty good for self-study. It's got some exercises, good explanations, and it has answers. Smells amazing. It's Matrix Algebra for Engineers. Until next time, keep doing math. Also, before I forget, check out my courses. I have courses on Udemy, but if you get them, use my website, mathsorcerer.com, or any of the links in the description of any of my videos. I've got tons of courses on math, right? All kinds of math courses, calculus, algebra, trig, advanced calculus, abstract algebra, etc. They're on Udemy, but again, use my links. Subscribe if you want. And yeah, that's it. Until next time, keep doing mathematics.